All right, today we're going to dive into one of the absolute cornerstones of power electronics. It's this powerful, really efficient component that, quietly drives our modern world, the three-phase bridge rectifier. It doesn't get all the headlines, but let me tell you, without it, so much of the tech we rely on every single day just wouldn't work. So here's our roadmap for this explainer. We're going to start with the basic problem, then I'll introduce you to the standard solution. After that, we'll break down exactly how it works. We'll visualize its output, crunch some numbers to see how it performs, and finally, I'll give you the verdict on why this thing is the absolute professional standard. You see, it all starts with this fundamental challenge in electrical engineering. The power grid gives us alternating current, or AC. But a massive chunk of our advanced technology, it needs huge amounts of, and this is the key part, stable direct current, or DC, to function. And this isn't some abstract problem we talk about in a classroom. We're talking about the real world here. The core challenge is turning that AC from the grid into super smooth DC for things like the fast chargers for your electric car, the massive power supplies for data centers, and those high-precision motors you see in industrial robots. So the big question is, how do we do this conversion efficiently and reliably, especially at a huge scale? So how do we tackle this conversion problem? Well, we turn to the industry's go-to solution, the three-phase, six-pulse, full-wave bridge rectifier. It's the undisputed champion for high-power stuff and for some very, very good reasons. So here it is, the circuit itself. Now, at first glance, it just looks like a simple bridge with 6 diodes. But as the professor's insight here points out, you've got to think of this differently. It's not 6 separate parts. It's a single, elegant, coordinated system designed to do one thing perfectly: carve out the smoothest possible DC voltage from those incoming AC waves. Okay, now for the really cool part. How does this coordinated system actually do its job moment by moment? Let's deconstruct the whole mechanism and take a close look at the conduction sequence. The entire operation, as complex as it might seem, really just boils down to one simple but incredibly powerful principle. At any given instant, the circuit just asks itself a question: which pair of input lines has the biggest voltage difference right now? And whichever pair that is, the 2 diodes connected across them get forward biased and start conducting the current. Simple as that. So what's the direct result of that rule? Well, it means that at any instant, the circuit intelligently picks one diode from the top group, that's D1, D3, or D5, to connect the load to the most positive line, and one from the bottom group, D2, D4, or D6, to connect to the most negative line. It's constantly making the best choice. This table here just illustrates that sequence perfectly. Look, for the first 60 degrees of the cycle, the line-to-line voltage VAB is the highest. So what happens? The circuit turns on diodes D1 and D6. Then, as the AC phases rotate, VAC becomes the dominant voltage, and the circuit switches conduction over to D1 and D2. And this just keeps going, handing off from one pair to the next every 60 degrees. This circular diagram gives us a great 360-degree view of this seamless handoff. It's like a perfectly choreographed relay race, where the baton of current gets passed smoothly from one diode pair to the next. This makes sure the output is always connected to the highest voltage available at that instant. And that continuous handoff, that's the secret sauce to the high-quality 6-pulse output. Okay, we've gone through the mechanism, we get the handoff. So what does the output of this whole elegant dance actually look like? Let's visualize the waveforms and see the result. Over here on the left, we've got our standard 3-phase AC input. Nothing new there. But look at the right. That's the result of the rectification. The rectified DC output voltage is basically just the top envelope of all the positive line-to-line voltages. So the key takeaway here is that the output is always tracing the peak of the incoming AC, which creates a much smoother and much higher average DC voltage. Now let's zero in on 2 critical characteristics here. First, unlike a single-phase rectifier, the output voltage never, ever drops to 0. You get 6 pulses per cycle. Second, the output ripple frequency is 6 times the source frequency. And as the insight says, this is a huge practical advantage. Why? Because a higher frequency ripple needs much smaller, and therefore cheaper, inductors and capacitors to filter it out into pure DC. But remember, voltage is only half the story. The current waveforms are just as important for us as engineers. The current that gets pulled from each supply line isn't a sine wave at all. It's this quasi-square shape you see here. And even more importantly, look at the current through a single diode. Each diode only conducts for 120 degrees. That's exactly 1/3 of the total cycle. This is an absolutely critical piece of information for managing heat and picking the right components. So we've seen the waveforms, and yeah, they look pretty impressive. But how does this circuit actually perform when you put numbers to it? Let's shift gears from the qualitative to the quantitative and run through a practical case study. So we're going to analyze a typical design with a simple resistive load. Our givens are an output DC voltage of about 280 volts, a DC current of 60 amps, all coming from a 60 hertz source. Our goal? To calculate those key performance metrics that really define the quality of this power conversion. And the first result from our analysis is, well, it's pretty remarkable. We're looking at an efficiency of 99.83%. I mean, that is a near perfect conversion. It means that basically all the AC power you pull from the source gets delivered as useful DC power to the load, with almost nothing lost. Next up, the ripple factor. This is our measure for how smooth that DC output really is, and the number is a mere 4.0%. This number just confirms what we saw in the graph. The output voltage is incredibly stable with very little of that unwanted AC ripple. And finally, the power factor, which comes in at a very high 0.956. This tells us the rectifier is drawing power from the grid really effectively. It's not wasting a lot of reactive power. You put these three numbers together, and the evidence is overwhelming. This is a highly efficient and incredibly effective circuit. Now look, these calculations aren't just for an exam. They have direct real-world consequences. This pro tip shows you exactly how they guide our design choices. These numbers tell us precisely what our diodes have to be able to handle, the maximum voltage they need to block when they're off, that's the PIV, and the average and peak currents they have to carry when they're on. This lets us pick the right parts for a reliable design that's going to last. So, we've analyzed the theory, we've visualized the waveforms, and we've crunched the numbers. What's the final verdict on the three-phase bridge rectifier? The verdict is that this is so much more than just a circuit diagram. It is a fundamental building block of our entire modern technological world. It's working behind the scenes in renewable energy, in electric cars, in the data centers that run the internet, and in all kinds of heavy industry. It is, quite literally, everywhere. And if you need one last piece of evidence, this comparison table just drives the point home. Compared to a single-phase bridge, the output ripple is way, way lower. The ripple frequency is higher, which makes it easier to filter, and both its power handling and its efficiency are significantly better. The takeaway is clear. It's unambiguous. For any serious, high-powered job, the three-phase bridge is the professional standard, period. So, we've now mastered how to efficiently and reliably convert AC to a fixed DC voltage. But achieving this mastery leads us to one final crucial question to think about. What happens when we want to control that DC output voltage, to be able to vary it whenever we want, not just accept the fixed value this circuit gives us? Well, that, class, is the topic for our next discussion.